Welcome to video lecture 1, Speed. As we begin our study of physics, you may feel like you already know a lot about what we're learning. And in many ways you do. Forces and different types of motion are something that we all experience on a daily basis. The reason so many people think that physics is a hard subject is because math is involved. I don't know how you feel about math, even though I could venture a guess, but I would like for you to think about math a little bit differently as we talk about motion and forces. Most of us can describe how things move pretty easily when we're using words. We say things like, that's moving fast or slow, or that's speeding up or slowing down. Most of us could probably even give good directions to a friend who was trying to find our home. But when it comes to describing motion using numbers, I see a lot of students fall to pieces. I think this is because when you look at data tables full of numbers and start performing calculations, it's easy to forget that the numbers tell a story about the motion of an object just as much as the words we could use to describe the same motion. So why use numbers when we can understand words more easily? The beauty of numbers is that they are precise. They don't describe motion in a general way, they describe it in an exact way, in a way that words can't. So if you find yourself frustrated with numbers, remember that they have a meaning. Ask yourself, what story are these numbers trying to tell instead of just trying to plug and chug through equations on a piece of paper? It's a little bit like learning to read all over again. But if you find meaning in your math, your understanding of the science of force and motion will go through the roof, and you might even find yourself enjoying physics along the way. Go ahead and pause the video and record the essential question in your notebook on the next available right-hand page. It's pretty easy to describe something's speed with words because we do it on a daily basis. If I asked you to come up with a simple definition for the word speed, you'd probably give me the definition listed by the first bullet point on the slide. Speed is just how fast something moves. So how can we tell if something is moving fast or slow? Well, think of someone who can run really fast. Champ Bailey holds the record for the fastest 40-yard dash in the NFL Combine. He sprinted 40 yards in 4.28 seconds. That's fast. In the Marines, you have to run 3 miles in 18 minutes or less to get a perfect score on your physical fitness test. We think of animals like turtles and snails as being really slow because it takes them forever to go even short distances. If you think about it, it's really impossible to describe something's speed with any precision unless you also describe the distance that it traveled and the amount of time it spent traveling. When you describe the speed of a car, you almost always use the unit miles per hour to get a sense of whether it's moving fast or slow. We all know that a car moving at 10 miles per hour is moving slowly, and that a car moving at 100 miles per hour is moving really fast. The unit miles per hour reveals that speed, in math terms, is a rate. A rate is used to compare two different things. In this case, speed, the distance something travels, is compared to the time it has spent traveling. The mathematical formula for calculating average speed is right here. The average speed of an object is equal to the total distance it travels divided by the total time it spent traveling. If you drive 60 miles in 60 minutes, your average speed is 1 mile per minute, or more familiarly, 60 miles per hour. Pay special attention to the units when calculating average speed. They say a lot about how fast an object is moving because they represent how far it goes and how long it took. 1 mile per minute is relatively fast, but not nearly as fast as 1 kilometer per second. In physics, our standard unit for distance is the meter, and our standard unit for time is the second. The standard unit of measure for speed, respectively, is meters per second. Being able to describe something's average speed is good, but it's limited in its ability to actually describe how fast things move. For example, My wife just took a trip to Kansas City to visit her parents. It's about a 630-mile trip, and it took her about 9 hours to drive there. Calculating her average speed on the trip is simple. The total distance traveled was 630 miles, and the total time it took was 9 hours. 9 goes into 63 7 times, and bring up your zero, so her average speed on the trip was 70 miles per hour. While this gives us a general sense of how fast she was moving over the course of the trip, it doesn't tell us the whole story. I'm sure some roads had slower speed limits than the highways, and I'm also pretty sure she had to slow down because of traffic in big cities she traveled through. We have 5 children, so I'm willing to bet there were quite a few potty breaks along the way too, which means she had to stop altogether. Plus, she had to stop at least once for gas, not to mention stoplights and stop signs and all of that. Over the course of her 9-hour trip, it's reasonable to say that her speed was probably changing a lot. If we wanted to describe her speed during the trip in more detail, we could find her instantaneous speeds, the speed she was traveling at any point in time during the 9-hour trip. In the next lesson, we'll learn how to calculate instantaneous speeds, but for now it's enough to recognize that her instantaneous speed over the course of the trip changed a lot. Sometimes it was below her average speed of 70 miles per hour, sometimes it was higher, and sometimes her instantaneous speed was even 0 miles per hour. The combined average of her instantaneous speeds was 70 miles per hour. But she wasn't moving 70 miles per hour for the whole 9-hour trip. If she had been traveling at 70 miles per hour the whole trip, then her instantaneous speeds would equal her average speed. When that happens, when instantaneous speeds equal average speed, you can conclude that the speed of an object is constant or unchanging. Now that we know the difference between instantaneous speed and average speed, and we've described different ways speed can be represented with words, let's look at how it can be represented with a data table. The data table that you see below represents the motion of an object. First of all, if we want to describe the average speed of this object, recall that average speed is the total distance divided by the total time it takes an object to get there. So the total time that this object traveled was 5 seconds, and the total distance that it traveled was 10 meters. This makes calculating its average speed really very simple. The total distance being 10 meters, and the total time it took to get there being 5 seconds. 10 divided by 5 is not so difficult. The average speed of this object is 2 meters per second. In the last slide we discussed instantaneous speed, and I promised that we'd learn how to calculate it in the next lesson, but let's take a moment to investigate the instantaneous speeds of this object as it travels. Between seconds 0 and 1, the object has been traveling for 1 second. And during that 1 second, if we look on the right-hand column of the data table, it traveled 2 meters. If we were to calculate the speed of this object during the first second, again, it would be 2 meters divided by 1 second, a speed of 2 meters per second. Notice that this instantaneous speed is the same as the average speed, the total distance it traveled, divided by the total time it took to get there. Let's take a look at the second second. From 1 to 2, which is also 1 second, it traveled a total distance of 2 more meters. It went from 2 to 4 meters of traveled distance. So again, we could repeat this same calculation. The speed of the object during the second second of its motion was also 2 meters. From 2 to 3, that's another travel time of 1 more second, and it traveled From 4 to 6, that's 2 more meters. Again, an average speed corresponding to an instantaneous speed at second 3 of 2 meters per second. During the next second, from 3 to 4, it travels another 2 meters. And so on until we get to the 5th second. So here's an example that I cited from the last slide, where this object is moving at 2 meters per second for the entire 5 seconds that it's moving. Its instantaneous speeds, right here, are the same as its average speed. What we can say about the speed of this object, based off of the story that this data table tells, is that it is moving at a constant, unchanging speed for 5 seconds, with an average speed of 2 meters per second. The last thing that I'd like to do in this video is represent speed using a graph. So I failed to mention in the last slide that the distance the object travels, how far it goes, is always going to be the y value in a data tabling graph. And the time that it takes to travel, or how long it takes to travel, is always going to be the x value in your data table or graph. So this first data table is the one that we saw on the last slide. It described the constant speed of an object that traveled for 5 seconds with an unchanging speed of 2 meters for every second. So graphing this is not difficult. We'll use these red dots in the left-hand margin to fill in our data table. So our first data point at 0 seconds is a distance of 0. So that's the origin of our graph, 0, 0. The first second of travel, this object has gone 2 meters. So on our graph, second 1, by the way, the interval of this graph on the y-axis, the interval is the tick marks, every line represents 2 meters traveled. So this 5th line is meter number 10. During the second, we've gone 4 meters, so we'll take this to 4. The third second, we've gone 6 meters. The 4th second, we've gone 8 meters. And the 5th and final second, this object has gone 10 meters. So, you guys are in algebra, or most of you are in algebra. You can see that the slope of this line has something to do with the speed of the object. Most of you know that slope is rise over run. y2 minus y1 over x2 minus x1. Well, let's look at the slope of this line. The rise is 2 meters and the run is 1 second. 2 meters over 1 second gives us a speed of 2 meters per second. Just like the density lab that we've done in class, the slope of a line on a distance time graph will tell you the speed that the object is traveling. Now, average speed is total time and total distance. So if you're looking at a graph and trying to calculate average speed, all you have to consider is this last point. How far did the object go and how long did it take to get there? You can use that last data point to calculate your average speed. Let's take a look at this second data table. The values are slightly different. Just like the first data table, at 0 seconds the object has gone 0 meters. At 1 second, the object has now gone 4 meters. So let's go ahead and graph that. At 2 seconds, the object has gone 8 meters. At 3 seconds, the object has gone 12 meters. And at 4 seconds, it's gone 16 meters. And by the 5th second, this object has traveled 20 meters. So, if we take a look at the slope of this graph, what do you think? Is this object traveling more quickly? Is it moving faster than the first object? What is the slope of the line that we just graphed? Well, if slope is rise over run, In this case, the rise is 4 meters and the run is 1 second. 4 meters and 1 more second. So 4 meters divided by 1 second. This second object is traveling at a speed of 4 meters per second, twice as fast as the first object. So one takeaway from a graph is just by looking at the slope of the line for the moving object, you can tell how fast it is going. The steeper the slope of the line, the faster the object is moving. One special case. Let's pretend for just a moment that we have a third data table. So we'll cross out these distances in the second data table. Let's pretend at 1 second the object has gone 0 meters, and at 2 seconds the object has gone 0 meters, 3 seconds 0, 4 0, and 5 0 meters. This object has traveled 0 meters. What would our graph look like in this case? Well, again, like the other graphs, it starts at 0 0, but after 1 second the object has traveled, again, 0 meters, and 2 seconds, my slope got off there, 2 seconds the object has traveled, we'll just move it out of the way, 0 meters, 3 seconds, 0 meters, 4 seconds, 0 meters, and 5 seconds, 0 meters. The slope of this line is 0, it's a flat line. Whenever you see a flat line on a speed time graph, the object is traveling at 0 meters per second. Another way of saying that is the object is not moving. The object is at rest. Let's go ahead and put that second line back. Thanks for watching.